Okay, I think yeah, it's 2 p.m. and let's start. All right, everyone. I just want to share my screen. And all right, I hope you can see my screen. Okay, I just want to quit this one. All right. So hello everyone. So I am Furkan, a PhD student in Dr. Smackton lab. So today actually I will explain how cell cycling, death, and secretion and uptake is carried out in PhysiCell. So Aneequa actually explained the the motility mechanics, volume, and microenvironment, and also briefly talk about the DTs. So therefore, I'm just going to the cycle one, and in PhysiCell, each cell has phases and phase lengths and the cycle model. And the cycle model has phases like you can see in here is leave, and the phase length is a transition rate between the phases. And this phase transition rate can be specified and can be defined. And also we have arrest functions that could be very useful if we want to uh, arrest at one transition to the others. So for instance, let's say if there is a less concentration of the oxygen and we want to limit the cycle to change the transition, we can just assign the arrest function and arrest this phase and limit the cell like this. And the cell data stores the cell's current transition rate. So the cell cycle is again run by the phenotype, and phenotype dt is 6 minutes. And also, I just want to remind that cell uh, phase changes are occurring stochastically as a default. You can change it if you would like to, but it is actually looks for the it multiplies by the transition rate with the dt and looks for the probability. And so the transition, when we say transition rate, it is actually a unit of per minute. And when we, as an example, when we define the phase transition rate to 0.0166, it means that the phase duration rate is 60 minutes. If it is this, yeah, and this is kind of again occurring stochastically in the as a default in the simulation, but we can also use the fixed option to just set this variable to the specific value. So PhysiCell has some number of builded phase the cycle models, which is leave Ki67 basic, advanced flow cytometry separated, and key cycling phases Keysen. So those are kind of like how many phases are there and how many phase links are there, and which phase is just which phase link is just used for the division. So each cycle model should have a dividing phase link. Therefore, cells can divide. So so how we define this cycle? So there are two ways actually. The first one is defining the phase transition rate. So so this is the where we set like 0.016, or we can just give the phase durations as a kind of like a, in the unit of minute. So actually we have an example. If we use a live cell cycle which has only one phase and one transition phase link, so we can just setting in here to 0.002. And again, because this is a C++, the index is starting from 0. And because there is only one phase, the rate start index is 0 and end index is 0. But if, for instance, if we have a K69 basic one, we should have at least we should have two phase transition rate, to 0 to 1 and 1 to 0, and 1 to 0 will be the dividing part. And again, it's very similar. Similar in here, phase duration is just duration index, and if it is the fixed, then this should be true. And because we will use a user interface, these kind of like parts are just a Boolean checkbox. So let's go to the cycle app we have. So actually I logged in, and this is how it looks like. So in here, we are using flow cytometry separated, which has four phases and four phase transitions. And so we have basics as a normals. And so in here, there are two different types of seeding method. The first one is just seeding one cell, and the second one is just seeding two cells, not two cells, sorry, as a kind of like blob of cells. And each transition rate can be defined. So let's run a little bit and see the results first. So this is again, we have the flow cytometry colors in here. The start index is G0, G1, and there is a transition rate which is R01 to the S, and so in here actually we set the each transition to the 60 minutes, which is one per minute in a per minute unit. So when we increase this one, so in each hour, it should change the phase. And as you can see, it changed the phases, and it should go to the G2, and then it divides in the M, after the M phases. So this is how it looks like. So to see the behavior of the kind of like stochasticity, let's seed as a kind of like blob of cell and see how they behave. So this is a blob of cells, and so when we go to here, like as you can see, some of them are actually kind of like lucky to change the phase without waiting 60 minutes. So as you can see, like they are also dividing and changing the phase transition. So this is kind of like stochastically make it. So also we can just, for instance, like let's make the first two transition rates as a kind of like fixed. Okay. Yeah, it's generating the results. So they are waiting for an hour and then they change. And they are waiting for the second hour and then they change, and the other ones are not fixed, so therefore they are just changing. So okay, let's try the arrest function then. So in here, in the microenvironment, as you can see, we initialize with 20 millimeter mercuries, and when we said that if the oxygen is not greater than the 24, then just arrest this phase transition. So okay, so because the oxygen is always like 24 to 20, and the oxygen threshold is 24, they cannot pass the other to the other cycle phase. So let's make a kind of like an oxygen gradient. So this was kind of like an seeding oxygens like the 20, but so we wrote a kind of a function that is making a gradient of the oxygen and how it, let's see how it looks like. So also I would like to show the substrate level too. Okay, so in here, what you are seeing is the oxygen level is in here 38, and like it's actually decreasing, and this is 10. So just a reminder, the 24 was the threshold. So these two areas actually passing that threshold. So therefore, these guys cannot have an oxygen that is higher than oxygen. Therefore, they are not cycling, and so therefore we can have a kind of like we can arrest the functions. So I will not go through the all arrest functions in here, but we can write arrest functions according to the some secreted chemicals or a pressure. Pressure is just calculated by the others actually. So that makes that maybe we can use pressure if yeah. So in here, so I just actually gave the pressure as 1. Um, okay, let me go here, and it because it's making this. Okay. So what we are seeing is here. So the fourth one, the fourth cycle cannot actually go to the here. So so this is the pressure threshold. So the pressure is calculated by the other neighbor cells, and because these have a pressure that is higher than that threshold, they cannot divide, but the other outer cells can have a chance to divide. And also volume is kind of like similar behavior because of the adhesions, and so the volume is kind of like sometimes like small, and they cannot divide in the cell. If we have any questions, I can take in this one right now. Let me. Aneequa, can you help me?
Yeah, we have one question,
Mhm.
which is, does PhysiCell offer default cell types like helper T cells, drag, etc., with defined cell transition in the presence of, for example, a cytokine?
That's a great question. So I believe we don't have a library of type of cells, but it was a kind of like in somewhere in the roadmap and with as literature based values, but in right now we are just defining ourselves like manually.
Yeah, you can set those if you want that for your simulation, but they are not provided, like they are not out of the box. But
Yes.
obviously, you can implement that easily.
If there is uh if there is no question, then I will just go to the death model. um so so in PhysiCell, actually we have two different death models. The first one is the apoptotic, and the second one is the necrotic. And the apoptosis is just a phase that is just removing the cell, and necrosis is just a two-phase, actually kind of like very similar to the cycle model. It's a kind of like two-phase death model. And the first one is the necrotic cells. When the necrosis occur, they are just swelling, and then after they reach the rupture volume, that is a reference to the Aneequa's presentation. When they reach the rupture volume, and then they just shrink and lysed, and so how we define is look like this. So we are defining the death rate as again, it's very similar. You can use the phase transition rate, or you can use the phase duration um, in the model. Also, the necrosis is just again very similar thing. So the one thing I would like to explain is the apoptosis is very similar to the cell changing the phase, phase change, and instead of they are dividing, they die, and they are losing their volume according to the biomass change rates and fluid change rates, which are kind of like defined in the death model. And in the necrosis one, so we are using actually oxygen based necrosis. In this one, actually there are two different thresholds. The um, first one is the a kind of like the first necrosis threshold, and second one is the kind of like maximum threshold. So and it is based on the current oxygen level, and this is the first one. If the oxygen level is kind of like passing that part, then it's become a maximum one, and then it's a kind of like increasing the next necrosis rate. So let's go to the death model if we don't have any questions.
No, we don't have any active questions. I'm just answering them.
Okay. Again, in the death model, actually we have we have a blob of cell that are dying according to the um, type of death. So if you would like to use the apoptosis, then it should be 1. Or if we see the cells with a necrotic death, then we should use the um, second second option. So let's use this one firstly. So I would like to show the nuclei first. In here, the blue cells are apoptotic and green cells are necrotic. So where we are here is actually kind of a very similar thing. So the apoptosis rate is, if it is this one is just 666, then this means that they are dying in 60 minutes. They starting to die in 60 minutes. And so again, this is a kind of like stochastic tra transition rate, but we can fix it too. So yeah, in here it's very nearly to actually like they need to start dying um after the oh, okay, so this is 10 hours, sorry. So like it should be no 100 hours, which is so high. But some of them are passing that one by luck, and then they die accordingly. So the thing is I would like to show is the unlicensed fluid change rate is the parameter that is actually looking for the how fast they are losing their interest, their content. And actually there are 3 types of parameters that are affecting this losing the content. The first one is cytoplasmic biomass change, and the second one is nuclear biomass change, and third one is the fluid change. So actually we can see this one um, very for instance, like let's make this one a little bit bigger, so then therefore we will have more cells that are dying. So as you can see, they are losing their content. They are starting to lose their content in after the 10 hours. Actually, that's the transition rate that we set. Um, and so, for instance, when we make this nuclear biomass change rate very big, like maybe here, so what you will see is they will lose their um, nuclear part faster than the cytoplasm. So therefore we will see more kind of like orange instead of like dark orange. And we can change, we can set these parameters like this. Do we have any questions?
Yes, we have a question that you might like to answer.
Mhm.
Bernardo asked, the O2 mean in necrotic model, is it over all the cells?
Oh no, it's an oxygen. It's the oxygen value. It's the oxygen constant or density in unit of millimeter mercury.
Okay, then there's another question by Robert. Can we make the transition rate a function of concentration of substrates in the microenvironment?
Yes, we can actually change the transition rate based on that one. But I just want to remind that this is a kind of like, this is in the phenotype. So that change will be in each 6 minutes. So there are some, so you can write this function, which is kind of like related to the concentration. Yes, you can, but it will just update itself in 6 minutes.
Okay, and then there is another question by Farnosh.
Mhm.
Does this mean that we can model the content of the cell explicitly with our desired molecular details, and after apoptosis the molecules will be released?
That's a great question. So so I didn't cover the molecular part, but so yes, the internalized substrate will be in the microenvironment. Yes, of when they are dying. Actually, yes, they are
Yeah.
losing their.
And then there's one last question by James. How does lysed fluid rate affect apoptosis or necrosis?
That's a great question. So actually, so let's go to here. So uh, the the lysed is just, you will see actually kind of you will see a lysed and unlysed fluid change rate, and the lysed fluid change is affecting apoptosis, if I'm not wrong, but the lysed fluid change rate is just affecting this transition rate, and this one is unlysed fluid change rate. Okay, let's go here and let's go to the necrosis. So we actually like, and also if we change the cytoplasmic biomass change rate, it will affect the cytoplasm part, and like nuclear. So I will not actually like, I change the values in here very much. So I just want to refresh the NanoHub application and just have the default parameters. So let's have we have a necrosis part in here. So in the necrosis part, I just want to again explain the conditions in here. So so initial condition is just one, and Dirichlet boundary condition is one. So let's so in here the necrosis max is 2.5, and this is the value in the as a default in the PhysiCell, and the necrosis threshold is 5, where the necrosis starts. But this one is making the most reaching the maximum value of it. So let's make this one 4 point, or maybe let's make 5.1 to see the behavior. And okay, I would like to show. So in here, as you can see, actual cells are kind of like stabilizing according to the uh, physical forces, and because we actually see we have 5.1 in all domain, they are not dying, but they should start in here. Let's make it 4.9. So in here, so actually some of them are starting to die, and I just want to show that they are just first swelling, and then they are getting smaller and smaller after they reach the rupture volume, which is, I believe, 2 times of the radius. Um, yeah, so this is how it looks, and let's make it, this one is more faster, and let's reach to the maximum rate of the necrosis. So as you can see, because they are in the very low oxygen level, lower than the threshold, they are just um, starting dying after we seed. Um, yeah, that was the death model. If we don't have any questions, then I will just go to the secretion and uptake. And
Yeah, you can go. There's no question right at the moment.
okay, thank you. Okay. In the secretion, so actually this is the main formula of the bioFEM that is just solving in each DT. So this is again PDE. So this is a kind of like point of voxels. In each voxel we have a diffusion, we have a decay, and we have a cell secretion or uptake or export rates. So we are not covering those ones. We are just focusing on this part. So so this part is the, oh sorry, let me go here. Right. Ugh. Okay. Okay. So as you can see, this is a secretion part. So for the secretion, we have an S, which is the secretion rate constant, we call secretion rate, in the unit of per time. And we have a saturation density that is just a kind of like maximum threshold of the concentration of the substrate in that voxel. And also we have a current current one. So the secretion is kind of like subtracting the target value and then multiplying by the secretion rate and then the volume of the cell. This is how secretion works. And for the uptake part, it is just actually consuming some values based on the uptake rate and the current concentration. So therefore, like, cells can just consume or take their substrate to their self. And also there is a net export rate, which I will explain in a minute. So actually there is an option for the PhysiCell to look for the internalized, to monitor the internalized. So this is a substance actually in unit. It's a substance per time. So therefore we should have a substance per time. So what we are doing is here, this is a concentration and this is a per time. So then we are just we need to multiply by the volume to have a substance per time. This is true for the uptake too. So therefore, we are just monitoring the cells as a substance, which is called internalized substrates. And the net export rate is actually coming in here as a handy. So in here, the secretion rates and the uptake rates are kind of like tend band with the volume. But if we would like to use a net substance per time, we can just use as a net export rate. Let's say like just actually this could be positive and negative. If it is the positive, that means that it's secretion. If it is a negative value, then it means that it's an uptake. Yeah, if you have any questions about this part, I am very happy to answer it.
So there's a question. The empty circles are multiplication symbols.
Yes. It's a matrix multiplication, I believe, because this is a vector of uptakes, like number of uptakes, and this is the concentration of vector too. Oh, it's pointwise. Yes, I'm sorry. I'm so sorry. Yeah, this is a pointwise.
The vector multiplication. Yeah.
Oh no, it's a pointwise because this is a value.
Yeah. Like, these are vector. There's no matrix here.
I'm sorry. Yeah. Vectors, eat vectors, and get vectors. No, this is a just pointwise multiplication. I'm sorry. I'm wrong there. And yeah, we explained the net export, and the secretion depends on volume. So the secretion part look like this. So as you can see, we are defining, this is again a phenotype, and there's a secretion attribute, and the secretion attribute is just defining the secretion rates for the cell, and secretion rate for the chemical that should match the name in the microenvironment too. And in here, the secretion rate is 0, the secretion target is 0. So this is actually basically is not doing anything, but just a show. So if the secretion rate is defined and the target secretion is 0, then there will be no secretion because it's 0. So let's go to the application. So in this application, actually, there are 3 types of cell, which are 3 cells actually. The first type of cell is chemical A. It uptakes the chemical A. The second cell is secrete the chemical B, and C is the chemical C, but it's using the export rates. And also because we can have kind of like internal reactions to balance it. I just want to show that the track in agents should be on if we would like to track the internalized part. So let's simulate it. So this is the long one. Okay. So right now, actually, I am using the local version of this the application, which is I need to actually, for the Windows, I need to write the cell frames. It's not looking actually, it's not computing. It's in the Windows, but it's work for the Linux and Mac OS. So in here, so what we are seeing is the first cell is just consuming this chemical A, and let's go to the chemical B, which is just secreting some chemicals. And in this chemical C, it is again actually secreting some chemicals because the net export rate is positive. If it is the negative, then there should be it should actually consume, it should uptake. And also because we have the track part is enabled, we can actually calculate the the internal part of the cell. Okay, so what you are seeing in the left, this is the internal chemical A, and let's go to the chemical A first. So in chemical A, the by the way, the cell volume is the default cell volume, and therefore there is a difference between the there's a difference between the export rates and the secretion rates. Because of the formula, if we have the volume as 1, then just secretion rate can be used for the export rates, but it's a kind of like unlikely part, because it's the volume cannot be like 1 micron, cubic micron. Okay, so let's go to here actually. So this is showing the internal amount. This is not a concentration. It's an internal amount, and it's the internal chemical A is increasing by time, and while this is the normal line, not the dash line, is just total extra substances, and the dashed one is this one is total extracellular, and the dash one is total whole domain, like also the intracellular. So I just want to show that the mass is conserved there. Yeah, so in here, it is actually like taking the substrate, one substrate, in 100 time, because in 100 minutes, because this one is very, very low. Yeah, Tarut, that's a great question. So the first one is uptake, the second one is secretion, and third one is the export rate. So this one is uptaking, secreting, and also exporting, but also this is secreting. And okay, and then let's go to the B, which is the secretion. So we have seen that in the temporal-spatial graph, it's increasing the substrate, as you can see. So let's go in detail. So this is the internal part of the cell, which is the second cell, and they are actually secreting the amount of chemical B, and in the domain it's increasing because it's secreted, and also are the tile of the plots wrong? What do you mean, Farnush?
Actually, the titles are right. They are for the cells. So left cell, middle cell, and the right cell. And each cell is associated with one chemical, chemical A, chemical B, chemical C, respectively, and either they are secreting or absorbing it. So that's how these graphs are arranged. If you have a question, can you please ask? Like,
Yeah, so the left one is chemical A, which is updating. B is secreting, the middle, and C is just export. Let's use actually a negative export rate. Because this is a kind of like a special version of the code, you need to update this calculations. Yes, that's correct. Okay, so I just want to explain the first and this question, because it's confusing, because it shows extracellular concentration line in the plot that is titled in internal. Yes, that is correct. So this is, yeah, maybe I should name them different, but the left one is the internal and right is the external, and maybe just don't look at the title. The
Reason,
left is,
yeah. The
yeah, the
reason these are
left
a
is
bit confusing is because the amount of chemical inside the cell is much smaller than the total amount in the domain. So we
mhm.
needed to find that was the reason why we represented them in this way. So we needed to have two different legends for them. So on the right side, the red one, this is for the internal ones for all of them, and the blue lines are for the external ones, and this is how it is explained. Maybe we can add different more explanation to it at some
Yeah,
point.
yeah, maybe I should put some access names there too. Yeah, that's thank you very much. So okay, I just want to explain the Connor's question. Can you define export? Sure. So we have a secretion and we have an uptake rates, and those uptake rates are in the unit of per time, because we are multiplying by the concentration of uh, the concentration of the substrate and volume to have a substance per volume. So be, because we don't want to make a more calculation about net export rate, especially for the molecular part. For instance, when we do flex balance analysis and when we create a number of cells and number of substrates, number of substrate as an amount, we don't want to calculate based on we don't want to change the secretion rate based on the volume or so. So we put this export rate, which is just a substance per time. Therefore, we are just using that value to secrete or to uptake. So this can be both secreting and or uptaking part.
Yeah, I can explain. Yeah, I would just clarify that there are two ways you can secrete. Either you can have a secretion rate or you can have a net export. So if you want your secretion based on the volume of the cell, you will use the secretion rate or uptake rate. And if you want it independent of the volume and just want per unit time, so you will use the export part. And for the export part, it can be positive and negative, and depending on either it's secreting or uptaking. I hope it clarifies.
Um, yeah. So as an example, I put a negative value in here, which is just behaves like an uptake. So what you are seeing is the internal amount in the cell is increasing because we set it as an uptake. That was the secretion part of
There's
the.
another question. Is the
Mhm.
export molecule in this simulation the same molecules and what is being secreted?
Yes.
Uh, so chemical A, chemical B, and chemical C are
Oh,
three
in this
molecules.
simulation?
Yeah, not in this simulation, like overall in the app. So there are three different chemicals depending on the parameter size, parameter values. The chemical C can be or secreted or uptake depending on whether export is minus or positive, but chemical A is always being secreted, being absorbed, and chemical B is always being secreted.
Yeah. Yes, Cecilia, I actually added this one to make it more more explanatory. So yes, I will update this this PowerPoint like in a minute after it's done.
So another question: Are the cell points are the cells point sources delta distribution in your equation?
The delta distribution is just looking for the index of it. So that's why we are using, I believe. So this means that actually like just looking for the index of the cell, and then just is it 1 or 0? If it is 0, then if the index value is not matching, so cells have no extent. What do you mean? Maybe you can, if you would like, you can just unmute yourself and ask.
Yeah, the cells are just completely point sources, so it's a singularity essentially.
Yes. Yes,
Okay,
it's a point source.
Yes, there's infinite density then at that point. Yeah, 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 I get it.
Yeah, well, maybe, yeah, that's a great question, by the way. If so, so I just want to show this one and to make everyone knows. So if, let's say, we have a very high kind of like a secretion rate in here. So I'm just simulating, okay. All right, so the thing is, because the internal part, oh, sorry, I need to update the cells. Okay, updated. It's calculating the overall ones. Okay, this is the part I would like to show. So because of the mass conservation and the secretion rates, the internal ones are just mathematically calculated. So therefore, the internal chemicals can go below 0 if you are not kind of like if you don't have any internal creation rates. So if they, or maybe if they are creating less level than the secretion, then you can just have a negative internal chemicals, which is kind of like odd. So I just want to show that this is a kind of like
Yeah, this is
a
just to keep in
behavior.
mind, be careful.
The Danielle has a question. The units in the first two terms in the bracket seems to have units substance time rather substance volume per time. So so this is a length, and length perhaps the from the volume of voxel. Danielle's question is again, the units in the first two terms in the bracket seems to have units substance per time rather than substance per volume per time. Am I missing the per volume? Perhaps the volume of the voxel.
Volume is being multiplied here. You can see VI.
Yes, and he's continuing with the delta has units of volume. I'm not sure actually about the delta.
Okay, then there is another question. We can explain that question later. So can we get a negative environment concentration if the uptake is too high? Yes. If your uptake is higher than the diffusion, and diffusion, like actually you are getting from the environment, from the voxel, And if your uptake is more than the before the diffusion, it can go to negative, but this will not happen usually because diffusion is faster.
I don't think so, because it is multiplied by the concentration of the current voxel. So therefore, this is minimizing, actually getting minimizing and minimizing. So therefore, you cannot have a negative.
But if you have negative export,
Oh,
you are,
if you play with export,
yeah,
yes.
then you
If
can do
play,
that.
yes. But with this term, no.
Yeah. So yeah, you cannot absorb in the negative, but if you get use the export part of the secretion, and you export negatively export, which means you actually import more substance than what is present in the microenvironment. Microenvironment can go into the negative, so you have to be careful there also.
Yeah. Yeah, that
John
was
answers
all.
the delta question.
Yeah.
Delta function is unitless.
Yes. So if we don't have any questions, then we can just, I believe, end the session. And the next session will be, there will be a break, a big break. And the next session will be starting from 3:30 p.m. Eastern time. And John will have a complete example that is covering the all phenotypic parts and the macroenvironment parts that you saw today. Yeah, thank you very much. And I hope to see you in 3:30.
Thank you.